Naming alkenes and alkene reactions. First one, we should see a cyclopentane and numbering. To give the cyclopentene the lowest number, 1 cyclopentene, and then we collect up our groups, 3 bromo and 5 methyl. Second one, we should see a 6 carbon chain with an ene, and again we want to number it to give the ene the lowest number. In this case it's 2, so we could show this as 2-hexene or hex 2-ene. And then lastly, alkenes are subject to cis-trans isomerization, and if we draw in the hydrogens, we can see that on the alkene carbons the alike hydrogens go in opposite directions, and so that is the trans stereoisomer. Next one up, we should see a cyclohexene, and again when the ene is located on carbons 1 and 2, you don't have to include it in your name, but you can if you want to. 1 cyclohexene, and then this group, which is a 4 carbon unit, sec-butyl. Cyclohexene, and the position is 4 sec-butyl cyclohexene. Covering the one directly below it, again it's a cyclohexene. And again we're going to number to make the ene carbons 1 and 2. And now we have another analogous 4 carbon unit off position number 3, so that becomes 3 isobutyl. And the I would count, this sec should be in italics, not relevant to this problem. This ene is again a 6 carbon chain, and we're going to have the ene begin on number 2, so it's again a hex 2-ene or a 2-hexene. And now drawing in the hydrogen shows that on the ene carbons the similar groups both go in the same direction, and so that's the cis stereoisomer. This molecule cannot be called cis-trans because the 4 groups on the enes, there aren't 2 identicals on each side, so we're going to have to use the EZ system. Before we get there, we should recognize that it's a pentene, and we're going to number it like so. And so it's a 2-pentene because that's where the ene begins. Collecting some groups, we have 2 chloro and 3 bromo. And then lastly, prioritizing those 2 groups on this carbon by molecular weight, and then prioritizing those 2 groups on this ene carbon by molecular weight shows that the highest priority groups are on opposite directions, and that is the E stereoisomer. This molecule is commonly called vinyl chloride. If we were going to systematically name it, it's an ethene, and it's a 1-chloro. Here we have just a basic cyclohexene. No need to number the ene number 1, it already is. This commonly called allyl bromide. If we were going to systematically name it, it's a propene, and it's a 3-bromo. And then lastly, this 4-carbon unit is butene, and or if you want, you can say 1-butene. For 2 through 6, number 2 just asks for some completions. And so when we want to make alkenes from alkyl halides, we would utilize an alkyl halide and a base. And what the base will do is abstract an H, not from the carbon which bears the halogen, but from adjacent carbons, and mechanistically elimination happens. As the halide leaves, and it could happen as an E1 or an E2. In this case, this is showing it happening simultaneously, so that would be an E2 mechanism. And so the answers are base removes a hydrogen, forming an elimination product, and the most substituted alkene predominates, and that's Zaitsev's rule. Number 3, we're asked to discern 2-methyl-2-bromobutane, what happens upon reaction with sodium hydroxide in water. So first step would be to recognize this is a tertiary halide. Second step is sodium hydroxide. Could be a nucleophile or a base, and the water solvent will promote ionization. Furthermore, in the problem, it asks you for the 2 alkene products. And so now you know it's going to be an E reaction, either E1 or E2. Back to the fact that it's a tertiary halide means in the first step, bromide leaves, forming a carbocation. And then the sodium hydroxide acts as a base to abstract one of those 2 hydrogens. And this carbon is equivalent to that one, but those 2 are different than this one. So the 2 possible alkene products could come from base abstraction of that hydrogen, and these electrons funneling in to make the alkene. And that would be the Zaitsev alkene. That was right in the first place. Like that. Alternatively, the base could abstract that hydrogen, and that would result in that alkene. This alkene would definitely predominate, and since it goes through a carbocation mechanism, then elimination, that is the E1 mechanism. To review that, that's just one species involved in the rate limiting step. So the carbocation formation would be slow and the elimination fast. So if we were doing kinetics, we would only be concerned with the fast step in our kinetics. Number 4, alkenes generally react by addition. Number 5 is just saying, do you know oxymercuration, demercuration results in overall addition of H and OH to an alkene in a Markovnikov fashion? And number 6 is the reagents for hydroboration oxidation are BH3 and THF. BH3 and H2O2, which results in anti-Markovnikov addition of water across the double bond. Number 7, we're dealing with hydrohalogenation without and with peroxide present. We should recall that that gives us the Markovnikov addition product, and this will give us the anti-Markovnikov. And those two are regiochemical isomers. So Markovnikov says whichever ene carbon has more hydrogens will preferentially get the incoming hydrogen. So the Markovnikov product is that where the bromine adds to the least substituted, or the carbon with the least hydrogens. And when we do the same system using peroxides, we get the anti-Markovnikov halide. And you are asked to propose a mechanism for one of those. The more straightforward one is without peroxides. Any mechanism should show all the lone pairs of the reagent. And as we've seen thematically, the alkene acts as a nucleophile, attacking the more electrophilic hydrogen in this case, displacing bromide. Forming the more stable secondary carbocation and bromide ion. And then in the rebound step, the bromide attacks the carbocation, resulting in that halide. And do realize that the carbocation is achiral, so the bromide would come in from either face. And so you would get a mixture of enantiomers. At number 8, you're just being asked, do you know that KMNO4 in base cold converts an alkene to a diol? So you simply draw the carbon skeleton without the ene and add 2 OHs across the ene carbons. In the reaction of ozone followed by DMS, that's called a cleavage reaction, where the ene carbons both get fully oxygenated. So now you redraw your carbon skeleton, except for you don't draw the ene carbons connected. You do draw a double bond from that carbon, now connected to O, and a double bond from that carbon, now connected to O. And to finish it off, we should realize that those carbons each had hydrogens, so showing the final dialdehyde product. Number 9 is you're asked about bromination. Overall, bromination adds stereo specifically in that the two bromines overall come in anti to one another. So in A, those two bromines are shown as syn, so we're not going to get A. These two bromines are shown as anti or trans to one another, so you will get B forming. And recall that you also will get B's enantiomer in an equal amount. So the best answer there would be D. And in this case, there's no chance of it being meso because there's no plane of symmetry. At number 10, You're just asked about epoxidation and knowing that an epoxide forms when an alkene reacts with metachloroperbenzoic acid, and an epoxide is a cyclic ether. In MCPBA, metachloro and peracid. And it's this oxygen that gets inserted into the alkene, and it would make a triangular cyclic ether we call an epoxide. Number 11, you're just asked about a hypothetical reaction that gives two possible outcomes in the manner of Markovnikov and anti-Markovnikov. And Markovnikov deals with regiochemistry. So if you get both Markovnikov and anti-Markovnikov, that's telling you it's not stereoselective, not regioselective. But it also tells you that the addition occurs syn. And syn refers to the stereospecificity, and if it only occurs syn, then it is stereospecific, so number 11 should be B. Number 12 is just realizing that oxymercuration, demercuration of an alkene results in overall Markovnikov addition to the ene. So the carbon of the ene with more hydrogens preferentially gets the hydrogen, and the other carbon gets the OH. So in that case, that alcohol would form. In hydroboration oxidation, you flip that regiochemical outcome, and so that alcohol would be formed preferentially. And in number 13, you're asked to show the product of this, which is going to be a halohydrin, and the halohydrin is a tertiary alcohol and a secondary bromide. And the first step, you're asked to complete a mechanism given some arrows, and the arrows look like that, and like that, and like that. So the first thing to recognize is this bromide is leaving as a negative. This bromide is going to end up attached to two carbons, and nothing happened with that methyl group. And this bromide will also still have two lone pairs of electrons and a positive charge. We can ascertain the positive charge because this bromine atom is gaining a pair, using a pair, but also losing a pair. So it's going to end up positive. This arrow is this new bond, and this lone pair and arrow is that new bond. And the fate of the bromonium ion when attacked by water is that the OH is going to, from the backside, open up the bromine, resulting in that after loss of a proton. On the Just for Fun page, you're asked to explain how this halide could result from this alkene upon hydrohalogenation. We previously saw that the mechanism would proceed to give that initial carbocation and a bromide ion, and carbocations are known to rearrange, in this case with a hydride shift. we can produce that carbocation, and the reason that would happen is because this carbocation and that carbon specifically is benzylic and resonance stabilized and much more stable than that one. And then in the rebound step, the bromide could attack the carbocation, resulting in that halide. In the next one, you're asked for a sequence of reaction. In the first case, acid catalyzed hydration would give us predominantly that Markovnikov hydration product. Oxidation of the resulting alcohol would produce that ketone. In the second one, beginning with the same alkene, hydroboration oxidation would produce the anti-Markovnikov alcohol, and then oxidation with the chromium reagent would likely give initially an aldehyde, which would be subjected and likely to become more highly oxidized into that carboxylic acid.